Hello all. In this video, we are going to check the remaining uninformed search algorithms. There are total 6 uninformed search algorithms. In previous video, we have checked breadth first and depth first search. In this video, we are going to check uniform cost search, depth limited search, iterative deepening depth first search, and bidirectional search. So let us start with UCS. UCS stands for Uniform Cost Search. It expands the node with the least total cost and it will be using a priority queue. So let us see the same graph which we have used for DFS and BFS. S is the start node and G is the goal state. Over here we have to check the path cost also. So you can see from S to A path cost is 1, from S to B the path cost is 5, S to C the path cost is 8, from A to D the path cost is 3, A to E it is 7, A to G it is 9, B to G it is 4 and C to G it is 5. So path cost is given in the graph. Let us start with the initial node, that is S. So how we will be writing the steps? So step number I have included first, then I have specified the open queue, and in open queue I will be writing the node and slash I will be writing its cost, and then we can write the closed and what action we have performed. So let us start with the step 1. S is the initial node, cost is 0, so that's the initial node. As S is not the goal node, we will move towards the step 2. So we have to add X child elements. So S is having the child elements as A, B and C. We will write along with the cost. So A is having a cost 1, B is having cost 5, C is having a cost as 8, closed will be S as we have expanded. Action we have performed as adding A, B, C. Now step 3. So as A is not the goal node, we have to check for the child node of it. So you can see A is having a child node as D, E and G. So you can see B and C will be as it is under step 3 and we have added D, E, G along with the cost. So D, E, G initially we have added at the end, we have expanded A and we have added D, E and G. Next you can see step 4 and how we have added D, E, G along with the cost. So to reach D the cost will be 1 plus 3. To reach E, the cost will be 1 plus 7. And to reach G, the cost will be 1 plus 9. That is from the A node. From S, A, D, S, A, E and S, A, G. Now we have to reorder the element because we are using a priority queue. So priority queue always have the data in the ascending order. So that's why D will be coming first as the cost is 4. Then B5, E8, C8 and G10. So that is our step 4. We have done the reordering of a queue. Next you can see D is not the goal node. So as D is not the goal node, we have to expand it, but D is not having any child, we can close it. So you can see under the step 5, we have just closed D without adding any child. Remaining elements under the queue will be B, E, C and G. Next we have to check whether B is the goal or not. So if B is not the goal node, we have to add its child. So we will add the child of B node under the step 6. So you can see under step 6 we have added child of B. So B child is G and we will calculate the cost of G using the path cost, that is 5 plus 4. So 5 plus 4 is 9. So path cost for G will be 9. So you can see G is added at the end. So B is expanded. Expanded node means visited node. Once we add the child node of that particular node, it is called as expanded node. Next you can see, so G is added with the cost as 9. Next you can see reordering, 7 step. So whenever we are using priority queue, always we have to order it in the ascending order. G9 just now we have added. So because of the reordering, E8, C8, then G9 and then G10. Next element under the queue is E. We have to check whether E is a goal node. As E is not a goal node, further child are not present. E we will close under the step 8. Next element under the queue is C. C is having a cost as 8. We have to check whether it is a goal node. As it is not a goal node, we have to check for the child. So C is having a child as G. Cost will be 8 plus 5, 13. So G13 is added under the Q. It is already in the ascending order, so no need to do the ordering again. Next element under the Q is G. So G9, that is our goal, we have reached. So we'll stop over here, and the path to extract that G9 is SADBEC, and goal is reached. The final path for this problem will be SBG with the total cost as 9. So that is a uniform cost search. It uses a priority queue. Next search algorithm is a depth limited search algorithm, that is DLS. Suppose the limit is given to your graph as 2. So same graph I have used where S is the start node, G is the goal node, and limit is given as 2. Limit 2 means after limit 2 we cannot move further. So we'll start with the stack over here. As it is a depth limited search, it will be using a LIFO queue, or you can say stack. So S is the starting node we have added under the queue. S is not the goal node, so child node we have to add. So over here, while adding the node, we are writing the depth also. So S is at the depth 0, and the child nodes we have added as A, B, C with the depth as 1, 1, 1. S is closed. Then we will check whether A is the goal node or not. As A is not the goal node, child element we will add, which is D, E, G. You can see D, E, G are added at the starting only because it's a stack. From where we will pop, there only we will push the element. So D, E, G are added along with the depth, and B, C was the previous element under the stack. So A we can close. Next we will check whether D is our goal node. So D is not the goal node. We cannot move further. Similarly, E we can check whether E is our goal. E is not our goal node, and the limit is 2. We cannot move further, so E we can close. Then we can see directly our goal is G. So over here the path will be S, A, D, E and G. That is how we can reach to the goal. So that's a depth limited search. It will go only up to the limit. After the limit, there are no child elements present. So over here we can reach to the goal node because limit is 2. If the limit is given as 1, we cannot reach to G because then we can go from S to A, B, C. We cannot move up to G if the limit is 1. Next search algorithm is iterative deepening depth first search algorithm, that is IDS. It searches with the increasing depth limit until the goal is found. So again, same graph we are using. S is the start node, G is the goal node. It will start with the depth as 0. So initial value for the depth variable will be 0. So under the depth 0 only S is the node which is present. S is not the goal node, so goal not found. Then we will increase the depth by 1. So previous depth which was 0 plus 1. So new depth will be 1. So we will add S in the queue. S is not the goal node, so we can add its child elements as A, B, C. As depth limit is reached, that is 1, we cannot move further. The output will be goal not reached. Then we will increase the depth by 1. So previous depth is 1 plus 1. So new depth will be 2. Now from S we can move to A, B, C, and then from A we can move to D, E, G. As it is iterative deepening depth first search, it will use the concept of depth first search. Deepest it will be going. So it will be first checking S. Then S is not the goal, so it will add the child A, B, C. Then A is not the goal, so it will add the child as D, E, G. So at depth 2 only we can add the child as D, E, G. D is not the goal, so we can remove it. E is not the goal, we can remove it. And further childs are not present, and depth is also reached, so we cannot move further. Next element is G. We have reached the goal. This is how the iterative deepening depth first search algorithm works. It uses a loop starting with a depth 0, and the loop will increase by 1 until and unless the goal is found. So over here the path found is S, A and G. The last uninformed search algorithm is a bidirectional search. So let us check for the same graph. Bidirectional search can use any algorithm for the searching technique. So first we will check with DFS, that is depth first search, from both the sides. So we'll start with the S node and we will start with the G node. So whenever you are saying bidirectional search, it will perform a forward search, that is from the initial state to the goal state, as well as it will perform a backward search, that is from the goal state to the initial state. So over here we will start with S in the forward search and we will start with G in the backward search. As S is not the goal node, the child nodes will be added. They are the A, B, C. Similarly, G is not the goal node, so child elements will be added as A, B, C. As you can say, A, B, C are the common point. So we can stop over here. Over here, the first meeting point will be A, which is there under our Q. So the search will stop and the path will be S, A, G. Bidirectional search also can use breadth first search strategy for performing the search operation. So it will be using a FIFO queue. So over here also there will be a forward search and backward search. So we'll start with the S node in the forward search and we'll start with the G node in the backward search. As S and G are not the goal node, we will extract their child element. So S is having child element as ABC and G is having a child element as ABC. You can see the meeting point is present, that is A, B and C. That means search can stop. The final output can be SAG or it can be SBG or it can be SCG. So that is about the bidirectional search. So in this video we have covered 4 types of uninformed search. So that's it from my side. Thank you all of you.